I'm going to start this video off by talking about the spinor, or spinner, however you want to pronounce it. I saw a good video on PBS Spacetime where they were explaining it. You can go watch that on PBS Spacetime to get more information. But the idea here behind the spinner is that you have something that's spinning around, but it's made in such a way that it spins around so many times, and then as it's spinning, it's kind of returning back to its normal position. But if you look at this drawing, you can see that all of these bands that are coming from the object, they're colored. And as this object spins, these bands, they're moving, but they don't get pulled all the way around with this. Once you go a certain distance away from the object, these bands do remain in the same zones. So I'm going to say, if you could visualize this thing, if you could grab half of it in one hand and half in the other and pull it apart, can this model a positron and an electron coming out of the black holes? And the spinor, many people believe that this is really a good model for the structure of electron, that this is what you have. And so I'm taking it a step further. I'm saying, are these bands of flux coming out of the black holes that are the electron and the positron? It's the same thing. It's the same flux. It's spinning because you have the spinor, and the vibrations are going along these lines of flux coming out of the holes. So now I'm showing you the gyroscope that has a spinning disk, mass, and motion. It's creating a gravitomagnetic field. If that disk is spinning on its axis and then the gyroscope is turning, that gravitomagnetic field is cutting, and it's going to be changing directions. You're going to have, if it was analogous to a magnet, like if you had a north and a south, it's going to be going north, then south, then north. Do you see? Now the model that I'm building, in this model, everything's related. It's a unified field theory. You have gravitomagnetism, you have gravity, you have electromagnetism, and you have the electric force. And the same way how you have a cutting charge is going to make a magnetic field, or a cutting magnetic field can make a charge. We already know, because the gravitational waves propagate at the speed of light, that a cutting gravitational field is going to cause this gravitomagnetic field. And so the idea is you have half and half. You have the gravity side and you have the electric side, and really they're one thing too, that if you have cutting of one, it's going to produce the other. So if this gyroscope is made to turn a certain way, flipping around, can this gyroscope generate a magnetic field? We know it has a gravitomagnetic field, but we're talking about an electromagnetic field. So here, if you imagine that this is the Earth, and this is the center of the Earth, and the Earth rotates around its axis, you also have the Moon orbiting the Earth. I don't know if I have the directions right here, but the center of gravity between the Earth and the Moon is not the center of the Earth. It's offset from the center, and the two are actually orbiting each other around this central point. And so the center of the Earth is orbiting around this point. So you have the Earth rotating, it's creating a gravitomagnetic field, and that gravitomagnetic field is going around in a circle, and it's cutting. Does this cutting gravitomagnetic field generate the Earth's magnetic field? Now, there are some different ideas. One was that, if you had a metal, electrons move somewhat freely through it. If you start spinning that metal, the electrons will try to stand still while you're spinning the metal, and so that'll create an electric current. when it's accelerating, you have the resistance that'll eventually be slowing them down. But when you start, so, there are some ideas that, maybe there's something like that that's causing the magnetic field. But really, I don't think anybody has definitively said how the Earth's core is generating this magnetic field. What's going on in there? I think it's because you have cutting gravitomagnetic flux, and we're going to be looking at the equations in just a little bit. But, we have this here where the gravitomagnetic flux is going around in a circle. But if you talk about the gyroscope that's spinning and flipping over so that the flux is changing, okay, you might ask the question, is that really what you need? And could the moon be doing this inside the Earth? Can you have, the core is spinning and it's rocking because the moon is going around? You have the tides, you have all this. So what is going on inside the Earth? And what is going on inside of a positron and electron? I'm modeling them that they're like vortices, like black holes, if you will. And you have flux, some kind of flux that's going around in a circle, and it's cutting, and it's inside there. So what's coming out, and the reason why I started this video with the spinor is because a lot of these problems in quantum mechanics, you have wave-particle duality. Which one to use and when do you use which? And, you have to think about it. If you had a moment here and there was flux coming out, let's say gravitomagnetic flux, and it was cutting, and this is going around in a circle this way, so the gravitomagnetic flux is cutting, that would create like a Lorentz force that would make gravity. But then what happens if somebody's moving, orbiting in this direction or orbiting in that direction? Doesn't that kind of offset the action of the cutting flux? And so you have to say, is it rather something that's cutting back and forth? And is it like the spinor? So I think in quantum mechanics, you have wave-particle duality. Which one do you use and when? Reality, there's an underlying equation, and I think when you go down to maybe the levels of space-time, you can look at it like there's nothing else there but the space-time, and this equation's defining it. And because these equations can be true for a particle and a wave, you might just be able to get both. It really can be both depending on how it is being observed. So that is something, food for thought. But in any case, the idea to get a unified field theory is that if you have a cutting flux and it's going around, this is not going to only generate the counterpart. Like if you have cutting gravitomagnetic flux, it'll generate the gravity, but it's also going to generate the magnetic field and the electric field. That this is all one thing. You have a positron and an electron. They're the particle and the antiparticle. They're a pair, and each one has four. You have gravitational, gravitomagnetic, electric, and electromagnetic, and it's all one thing. So here we go. We're using quantum mechanics. This symbol here, okay, what I'm doing here is I'm using this symbol to denote the magnetic moment of the electron. Okay, the electron has a magnetic moment. But it's very interesting that Planck's constant takes the form of a gravitomagnetic moment. It has those units. So we're going to examine the ratio of the magnetic moment to the gravitomagnetic moment. And if we put the units in, coulombs per kilogram, meters per second, or meters squared divided by second, meters squared divided by second, you put these units in, and you have 1 divided by, and it's not quite 0.707. It would come out to 0.71 using the measurements that we have, but I rounded this to 0.707, and I'm going to explain why. But right now, we're just going to say that this ratio is really 1 divided by 0.707. So this magnetic moment, okay, if you put the 0.707 and it like 70% of this, that's what the gravitomagnetic moment is. So you have an equivalence here. Okay, so I don't know if this number is just a conversion factor, but it really looks like this is an RMS value, that you have a cutting magnetic moment, and that cutting magnetic moment is generating your gravitomagnetic moment. So we're going to keep going here. Planck's constant is equal to energy divided by frequency. So we're going to substitute that into the equation. Okay, and because the frequency is being divided, it's really up here. So the magnetic moment times the frequency divided by the energy is equal to 1 divided by 0.707 coulombs per kilogram. I divided out these meters squared per second values. Okay, so to keep going, E is equal to mc squared. We're going to substitute that. There you go. Okay, we're going to keep on going. Take that m and get it up here. You're going to multiply both sides. So now you have the mass times your coulombs per kilogram times the ratio is equal to the magnetic moment times the frequency divided by the speed of light squared. So we're going to move everything around and get these units, and now we know that mass is equal to coulombs per kilogram times the frequency times the electromagnetic moment times 0.707 divided by the speed of light squared. Okay, so this is the equation. This is a true statement. It has to do with the ratio of the electromagnetic moment to Planck's constant, which takes the form of a gravitomagnetic moment. So we can go up here, 0.707 times your electromagnetic moment, coulomb per kilogram, is equal to H. That's the same thing that we started with. It's just rewriting it. Okay, that's what the ratio is. And 0.707 is what you use for an RMS value. And RMS is the root mean square. What that means is, let's say you had a coil and there was AC going through it. There's a point at which the current is at its maximum and the magnetic field is at its peak. Then it's going to go through the cycle and there's a point where it's going to drop down to zero. Okay? The RMS is the root mean square. That's like the average of what the average magnetic field would be over the cycle, because it's not going to be, the average is not going to be the peak and it's not going to be zero. It's somewhere in the middle. It's 0.707, and that's based off of a sine wave. You see, if you have something going in a circle, let's say it's cutting in this direction. When you come out here to the outer edge, the velocity, it's going this way. So if there was an observer here, okay, he sees the velocity in this direction. He's got the cutting, okay? But as this comes around, now the velocity is going away from him. He doesn't have any cutting because it's just going away. Same thing, it's coming towards him. So it's in a different direction. The Lorentz force works on the perpendiculars. Now, so what do you have? You have the cutting is at its maximum, and then it's dying down to zero. Okay, so you can use this for a velocity, okay, the RMS velocity, or you can use it for the field, the strength of the field. There's all different ways you can use the RMS, but that's the idea. And it looks like it's working out, and it's given us what we're looking for. Because if you have a moment, and let's say that moment, it's saying that the magnetic moment, okay, that the RMS magnetic moment is going to give you your gravitomagnetic field. Okay, so now we're going to keep on using quantum mechanics to define these relationships. We know the de Broglie equation, wavelength is equal to h over mv, or the mass is equal to h over the wavelength v. We're going to substitute that in. Okay, where are we at here? We got to 0.707. We're going to substitute that into the equation we made here. How did I do this? Let's see here. Wavelength V. Yeah, so your mass, okay, That's coming from over here. So the mass is equal to h over the wavelength v. So we're going to substitute that. Now we've got it substituted in, and we're going to work our algebra. Okay, this wavelength v, if you take the frequency divided by the velocity, okay, that's, if you have this here, what do you have there? That's the velocity divided by the frequency. So the frequency goes up here. We're substituting this v over f for this. And so now we got v times v. We got the frequency here. Now these frequencies, it's probably the same frequency, but we're going to leave it there just for now. And we're going to keep working our algebra. This v, this goes over here, the v's, so you end up with v squared over c squared. Okay, what does that denote? That's your magnetism. It's showing you that you have cutting. Okay, this is just like Maxwell's equations. When you have magnetism, you might have, QV divided by your 4 pi epsilon naught r c squared. That epsilon naught c squared is 1 over epsilon naught c squared would be equal to the magnetic permeability. So you could go ahead and put that up there. Now you've got your force of magnetism because it's relativistic static force. So it's showing you right here that there's cutting. Now if you keep on going, these frequencies, they're probably going to divide out. Okay, and what do you have? You have this equation. Okay, and we already know that this is a true statement. So that v squared over c squared has got to be equal to c squared over c squared, because it's not even there. It's got to be equal to 1. So now we know what the v squared is. Okay, so it's going at the speed of light. It's cutting at the speed of light. So you have a magnetic moment cutting at the speed of light, and that's going to give you your gravitomagnetic field. Okay, so if you're coming down here, here it is. You have the magnetic moment. It's going around, cutting at the speed of light. Now this can work. You're using quantum mechanics. This is a true statement. If you have an electron going around an atom, when it releases a photon, I'm going to say that these are not equal. And so it's releasing what? It's releasing a gravitomagnetic moment. And that's really what's going to generate your electromagnetic wave. That the charge, the gravitomagnetic moment, the magnetic field, and the gravity, all that it's all equal. That when the wave goes, you've got everything, and that they're all equivalent. And this is just like Maxwell's equations. It's showing you've got cutting magnetic flux is equal to your gravitomagnetic moment. Now, because this is going at the speed of light, it doesn't mean that this equation has to always be the speed of light. Apparently not. Apparently you could put values in less than v. Okay, so the idea is if it wasn't necessarily cutting at the speed of light, you're still going to generate a gravitomagnetic field. It's just not going to be as strong as what you have here. If the v goes down to 0, what do you have? You have no gravitomagnetic field. So it's cutting. You have to have a cutting magnetic field to generate this gravitomagnetic field. And of course, a cutting magnetic field generates a charge. So there's an equivalence between the charge and the gravitomagnetic field. So from what we saw, we can expect that when we draw electromagnetic wave, you have the electric field, it's changing. That's creating your magnetic field. It's changing. It's creating your gravitomagnetic field, because that's what the equation is saying. And the cutting gravitomagnetic field is going to cause a gravitational field. Now, the issue is, I have it drawn like this, a sine wave. Is it pulsed DC? The gravitational field, is it always gravity or is it anti-gravity? Do you get anti-gravity out of this? So we're going to keep on working, and we're going to look at different ideas. One idea is that the positron and electron are black holes. They're connected to each other, or you could say a black hole and a white hole, but there's flux coming out of both of them. And one thing I would like to say, and I don't know if anybody thinks about this or not, or if what's been done, but I think it's pronounced the Stern-Gerlach experiment. it measured the magnetic moment of the electron. Now, I'm saying that it's looking like that's an RMS value. If you take that 0.71 and you make it to this 0.707, you're looking at a 0.6% error in the measurement. And between Planck's constant and that Stern-Gerlach experiment, it's so close that it's really suggesting, I think, that it's an RMS. But you have to keep looking. I'll have to keep working and look at these units and everything and see if it can be like that. But that's what it looks like. But this is food for thought. Is the electron and the positron really a magnetic monopole? That means there's flux coming out of it, magnetic flux. And so how would that behave in the presence of a magnetic field? Well, the flux lines connect. Here you'd have flux being bent off. It seems like it would behave the same way as it would as if it was not a monopole. So I think that's interesting to say, that the electron is really a magnetic monopole. You have a lot of ideas with people trying to get anti-gravity. You had the Searle effect generator. The Searle used spinning magnets. And if you have a spinning magnet, that's going to suggest a gravitomagnetic field, and that they were going around in a circle. So you have a cutting gravitomagnetic field. And, there's people that they say they might have observed something or, maybe not. It's, hard to say, but there's people that say they saw something. And I think that the configuration of these magnets needs to be a little bit different. But it's possible that something may have been observed. And but there's more ideas. One idea would be, let's just say you have a plate and it's positively charged, and it has resistance, so the electrons are going to be all over the plate because they can't just flow out. They're caught in there because it has resistance, and this thing is spinning. Okay, well, that's going to create a magnetic field. But what if these charges, they really act like anti-gravity? Okay, we're trying to get more information and get these ideas here. So you have the Alcubierre drive that's saying if you have positive and negative mass, it'll make a thrust. And if it was anti-gravity, or negative mass, a capacitor charged up would really give you the same thing. So let's say you have a black hole. If you had a black hole and you had a positron and electron, one's gravity and the other's anti-gravity, when they get close, it's going to attract one and repel the other. So it's going to split the matter. The gravitational field will split the matter if it was behaving like that, because you would have space-time like it's pouring in here, and it's here it's causing the attraction, but here it's repelling. But the interesting thing is if this was going with the flow, okay, if it wasn't being held up there, like on the surface of a planet that's stopping you from falling, if this is going with the flow, it's really like there's no force on it. It's just going with the flow of space-time. So it could probably go into the black hole and come out no problem, hopefully. You say if this is gravity and anti-gravity, like if one had space-time coming out and the other one had space-time going in, how then can, mass that's made of particles and antiparticles, positrons and electrons, how is it that it can have gravity? And you have to understand that, when the particle, it's together, it's neutral, but you've got, this flow of space-time that would be like coming in to the black hole if they work this way. And you've got the particle here. It's spinning around. I'm going to go ahead and explain this a little bit more. Let's say the space-time was going into one and coming out the other. This flowing space-time, the flow would be more concentrated. The closer you are, the further away you get, less concentrated. So if there was an observer here, this space-time cutting through him, time is going to be dilated more when you're close to it than when you're far away. So it's got gravity. Okay. Also, these particles would synchronize up with other particles that are doing the same thing. Positron and electron, if they work that way. Here's a little bit of theory that's, if they do work that way. Let's say you had two boxes and they're both moving together and they're flying through space, two boxes. We're not talking about a positron and electron now, just two boxes, people in them, they're flying through space. So it'd be like the space is cutting through it this way. Those boxes are length contracted, but so's the space in between them. Okay? So if space was flowing out of one, now it's you have the lines coming out this way, they're also going out that way. But in between the two, okay, in between the holes, you still have the same thing. So you would have the length contraction. And for ones that are going the opposite way, two boxes, they'd be length contracted, length contracted. This length expands because they're length contracting as they're going further away from each other. So, if they're both on center and they length contract, now this is getting bigger. So same thing. When the flows are counter, it's caused the repulsion of the particle. Again, as I've talked about quantum mechanics, you have wave-particle duality. I think these either-or scenarios can come up. It's hard to say. Is what's really happening is that space-time is flowing out of one particle and into the other? Or is there something else that's happening? And you have to think about this. Let's say the space-time is not flowing into the particle. Like, let's say here's your particle. It's not flowing in, but it's going around. It's just spinning around. And in the center, it's spinning faster than it is on the outside. Well, now you've got the same thing. You've got more cutting here than you have out here. You've got more time dilation towards the center as you have out here. And that Schwarzschild metric is telling us that when the time is being dilated, that's what's equivalent to your gravity. That's what's giving you your gravity. So you have the same effect. But I think it might be both at the same time. I think that it's a vortex. And, but you have to look at it and you have to wonder exactly what's going on. Is gravity, you could look at it all kinds of different ways. Is it pressure? Is it heat in the space-time? And it's a very complicated problem, but we're going to keep on working. And I think we're doing real good. But we've got this idea, if you have a gravitomagnetic moment, you have a mass that's spinning around and you've got this gyroscope set up so it can make all different kind of spins. Can that make a magnetic field? And the equation is saying yes, to the best of my understanding. Now you have the same thing. You have to say, if the equation said that a cutting magnetic field is creating this gravitomagnetic field, well then likewise would not a cutting gravitomagnetic field make a magnetic field? And so that magnetic moment that's inside there might, like that, let's say you have a magnetic moment and it's going around in a circle, that makes the charge, it makes the gravitomagnetic field where you have Planck's constant and everything. What is the magnetic moment? The magnetic moment can be a gravitomagnetic field, okay, which would be like mass going around in a circle, and that's cutting, and that's what's creating the moment. So it'd be like you have this going around in a circle this way, and this is going around this way, and it's giving you what is like a vortex, where, if you ever saw water going down the drain, that beautiful pattern, there's all kinds of spirals inside there, and the whole thing is going around. And so here you have the same thing. You have, this cutting. Now, I think it's interesting if you had something like this, and we're trying to work off these equations. Let's say you had the magnets, and the magnets are coming like this, so you got the magnetic fields, but these are spinning. Okay, so now the spinning magnetic field, it's creating a gravitomagnetic field, and then this thing is spinning around this way, and this is spinning around that way. So these cutting gravitomagnetic fields are like with the Mach's principle with the universe. You see, it's going to make a thrust on the space-time because it's pushing off of all of the matter, that's the fields from all the matter that's coming in from the universe. Now, here's the question. Will magnetic field lines that twist in opposite directions connect or break apart? Okay, I think that's an important question because you have to have this twisting. The idea is you make this machine, it's spinning this way. You know, this one's, it can be, you can set it up to go whichever way you want. You want this to spin this way, spin that way, or you can have this spin this way or spin that way. But when you look at this structure and you say, if you make this, will this not make us thrust in space-time? Because that's what we're designing it for. And then you look on the inside, the flux is on the inside, you know, the spinning flux vortexing around, and on the outside, is this not like a positron and an electron if you could take them? And so you say, can't that positron and the electron make an Alcubierre metric? Can't a capacitor, you know, that when you're going to separate these two and stop them from spinning around, because, you know, the atoms, the electrons orbit the nucleus, or if you have positrons and electrons, I believe that the neutrino is a reduced mass positron, electron in orbit, and that all of the matter is really made of the positrons and electrons, that, you know, when they're spinning around and they're in sync with the gravitational frequency, you know, everything's working. But if you stop them from moving, and you set them up so one's apart from the other, you know, will it not cause this thrust? And this model right here suggests that it will, if the positron and electron are actually analogous to this. And so the work continues. You know, you have to say, you know, here's an electromagnetic wave. You've got the, is this charge really gravitomagnetic flux? Is it going this way, then it's going that way? The magnetic field, is it really, you know, space-time is going this way, then it's going, and so it's making like a smoke ring. Is this the magnetic field? You know, is the magnetic component really shaped like this? But I'm thinking that maybe it's both, that it's not just in this direction, but this also has a helical, and so this whole thing is like a toroidal vortex. But you have to keep working, and you have to keep on getting the information to put this whole thing together. But right now, I did a lot of work before, and I started out trying to model these as black holes connected together. And I realized that you have to really build the manifold, and I think I'm going to come back to that later. But, you know, the velocities of things that I was getting were very high, and I said to myself, it's got to be cutting flux. So I went right into this, and I went into the quantum mechanics, and so this is the unified field theory, and this is the equation right here. This is the equation that you can work off of. And I believe this is right here. All the secrets are right here, that you can get it out of here. Now, the idea, okay, you have to think about things. Like, I believe that these are vector velocities, and this has to do with, you know, what's going on inside of an electron. But if that electron is moving through space, you know, even though this is moving at the speed of light inside here, now it has to slow down because the speed of, you have a vector. Speed of light is constant. You have time dilation, everything else. So this all factors into it. But these relationships can define what's going on inside here. It can also define this. I drew for, you know, the Earth and the Moon. But let's say an electron is going around an atom. You know, this is also going to work for this. You have an electromagnetic moment, and it's in orbit. Okay, and it has the wavelength and everything. That's quantum mechanics. Now, if you have this H, if this is, you know, like an electric field, that there's an equivalence there, and you have charge, you're seeing that, what do you have changing? You have a ratio. of one to the other, okay, that's really what you have as a ratio. And when you're changing the velocity, you're changing the ratio. So you have to ask, is one really staying constant and the other one's getting bigger, or is one being transformed into the other? Now, you have relativistic mass of the electron. You know, if you're not talking about using this equation for what's going on inside, but you're using it to define the electron moving through space, then you're going to say, well, what do we know about that? We know that the charge to mass ratio of an electron changes. As it goes faster towards the speed of light, it becomes more and more massive. So that's all part of this, and I'm going to keep working on it, and I hope you keep watching my videos. I hope you enjoy them, and I don't know everything, but I'm trying to get to the bottom of this, and I hope that you're learning something, and I hope you're not being pulling your hair out because of the mistakes that I made, because everything that I do, some of it's food for thought, but I really think that this video right here, that this equation, and you can come look at it up here, I really think that this is the value that's coming out of everything so far. So before we close it out, this question of the twisting flux, this is a positive. If this was like a positron and electron, you'd expect this to attract. Okay. Here's a north and a south, the magnets, the lines of flux. I don't know if it looks like this, but we'll say that, at some distance apart, that these flux lines are bending. And so we'll just stretch them into the perpendicular direction. That way you don't have to use sine and cosine and all that. But we'll just say there's a vector component coming here. Okay, now this one's spinning this way, this one's spinning that way. If you had an electron here, it's pushing it this way, or, whatever the sign would be. If you have the same charge particle electron, now it's pushing it this way. Okay. On this side here, this would be acting negative because it's pushing away the electron. On this side, this would be acting positive because it's pulling it towards it. So it would be like these attract each other. So I think that might be interesting, showing you something there, that twisting these, turning these in opposite directions increases the strength of the force. I think that's very important. That equation that I showed you where I set the frequencies equal, let's work that equation and say they're not equal. Okay, you can rewrite that equation like this. And what do you have? Let's say you had a moment, a gravitomagnetic moment, like a spinning mass, and that's coming around in a circle like this. It's got a wavelength. Okay, and then this is going like this. It's got a wavelength like that. So that might be the way to look at that, and it'd be generating a magnetic field. Now, if you write the equation, it's giving you, the frequencies, the velocities. You could probably work this. You don't have to put in the speed of light. Maybe it's part of it. You have to look at what the structure of this is. But you have Planck's constant. You're going to get a magnetic moment based off of this equation that's working, because it's showing you that the gravitomagnetic field, that it's when it's cutting, it's generating this. So you have Mars. Can a moon give Mars a magnetic field? It's got two moons, and they orbit at different frequencies. Well, where's the center of mass of the planet? How fast is it rotating? And, it looks like something crashed into the planet at one time. So that's something interesting. Terraforming Mars and anti-gravity and lots of other things, and finding out physics, what's really going on. So hopefully that this stuff all turns out to keep working, and that nothing happens to say, nope, we're hoping that this is all going to work out real good.